Okay, question 2. So they've got a triangle here, and first thing that I notice is that it's an isosceles triangle. Wow, my dog decided to start barking for the first time as soon as I turned my phone on record. Okay, so it's an isosceles triangle. I know this doesn't look like an isosceles triangle. We've got 30 degrees there and 20 centimeters here. So that means this is also 20 centimeters because it's isosceles. If it's isosceles, we also know that these angles are the same. So this is 30 degrees. And the question's asking us, what is the area of this triangle? Okay, so area, we're working with a triangle. It's not a right angle triangle. Straight away, I know I need to think back to the chapter in my textbook that deals with non-right angled trigonometry. And can I think of any formulas that are going to help me if we're trying to find the area? Yes, we've got the area formula. So you pretty much just have to remember that the formula for area of a triangle is half AB sine C. When we're dealing with angles and trigonometry, there is also half of the height times the base. But because we've got these angles here, that's a pretty good indication that we'll be needing this formula. Now, we also know that the angle sum of a triangle is 180. So if this angle's 30 and this angle's 30, altogether that makes 60. Well, this angle has to be 180 minus 60 because that's the only angle that's left and it needs to add up to 180. So that's 120. And now we can attempt the question because we've got, let's label our sides. So this C here in this formula is an angle. And this A and B have to be the two sides on either side of that angle. So these are the only two sides we've got. So it's a pretty good chance that we need this angle here, and that's going to be C. And the opposite side is going to be little c. And then these can be A and B, doesn't matter which one is which. The opposite of B, little b, the opposite of A, little a. So now we've got all our values, we can just plug it into the equation. So half A, and A is 20 centimeters. B is 20 centimeters as well. Sine C, and we worked out that C was 120 degrees. So that's it really, that's how we find the area. So we just need to plug that into the calculator. So we've got a half of 20 times 20 times sine of 120. And our result is 173.205, And it says our answers to the nearest square centimeter. So it's 173 square centimeters, and that's B. Let's have a look at question 8. I've decided to record my screen for this one because it doesn't really involve any handwritten calculations. It's more just about reading this graph and looking at it and then making an estimate. So, Josh collects data for two variables which he plots on a scatter plot and draws a line of best fit. So here's our line of best fit. Our two variables are L down the bottom here and M up here. And it doesn't really matter what they are at this point. So what is the likely correlation coefficient for the two variables? Okay, so because it says likely, that tells me I don't actually have to calculate the correlation coefficient, so I don't have to worry about formulas or anything like that. We're just doing an estimate because it's likely, the likely correlation coefficient. So let's have a look at our graph. Now, a correlation coefficient of 1 means that all of these little points are on the line. That there's a perfect correlation between L and M, and there's no scatter at all. And that's the same for -1, sorry. So correlation coefficient of 1 means that it's going to be a positive gradient and it's going to come up like a line through here, going up the staircase, it's increasing as we go further along this L axis here. And correlation coefficient of -1 will be a negative gradient like the line that we've got here, but instead of having all this scatter, all the points are going to be exactly on the line. So we want to now know, well, we've just said that it's negative, so we know it's either A or B, but we basically want to know whether it's a really strong correlation, or is it, a moderate correlation. And now in this case, this is this sort of graph here that looks like this with points that are really close to the line. Most of the points are really close to the line. That is going to give you a really strong correlation. So it's going to be in the 90s. And you sort of just have to practice with these questions and get familiar with the types of scatter because, you've got nothing to compare it to. So I can see why you might guess that. 0.59, but 0.59 for this graph is just far too low. Okay, this is actually got a really high correlation because those dots are quite close to the line. There's not much scatter at all. Because remember, a correlation coefficient of 0 means that there's absolutely no correlation and that they're just scattered all over the place, the dots. So we don't want to go anywhere near 0 for this line because it's quite strong. So that means I'm just going to be guessing something that's in the 90s, so 0.95, and we know it's negative because it's got a negative gradient. All right, so we're looking at question 13 now, and I've already drawn the graphs for us. I'll just write the equation as well, see if we can get everything on the screen. I can't really. I'll just write the equation down here. So it's y equals 3 to the minus x. Now, you might remember from your topic on nonlinear equations or nonlinear graphs that when you're looking at something like this, it doesn't matter what this number is, the line is always going to cut the y-axis at 1. And the reason for that is, well, we know the y-axis, that's this line here. So that's when x is equal to 0, okay? This line here is where x is equal to 0. So if we were to put x is equal to 0 in here and substitute that in, we would get 3 to the power of 0, or 3 to the power of minus 0, which is just 3 to the power of 0. And any number to the power of 0 is always going to be 1. So it doesn't matter what number you have here, even if it was 5 to the power of 0, it's still going to be 1. So any equation that looks like this is always going to cut the y-axis at 1. So you might remember that, but it's all right if you don't remember it because we can always test points as well. So that's what I'm going to show you how to do here. So let's have a look at our options. We've got two graphs up here that look the same. They're increasing as we go further to the right. And we've got two graphs down here that look the same in that they're both decreasing as we go to the right. So something tells me that's going to be to do with the sign of the equation. So see how we've got this negative x up here? If that was a positive x, maybe it's these ones which are going in a positive direction. And if it's a negative x, maybe it's these ones that are going in a negative direction. But let's just test some points and check it out. So if we want to look at the y-axis and determine whether, so the other part of this question is that these two are cutting the y-axis at 3 and these two are cutting the y-axis at 1. Now we just said that we know this is going to cut at 1, but let's just test it. So the y-axis is when x is 0. So if we just test and put in y equals 3 to the minus 0 because x is 0, we get 3 to the power of 0, which is just 1. So that means that y has to be 1. When x is 0, y has to be 1. So it has to be one of these, so we won't worry about these two. And now let's test a point to see if it's going to be this positive increasing one or this negative decreasing one. So we can test a point on either side. If we test a point here where x is greater than 0, so we could test x is 1 because that's greater than 0, or we could test x is 10. We can test whatever we want. As long as it's positive, we'll be checking this section here after the y-axis. And if we find a value for y that's greater than 1, then it has to be this graph here. Because if we look at this graph, when x is positive after the y-axis, y is actually less than 1 because as you can see, it's lower than 1. So let's check. Let's check a positive value on this side of the y-axis and see if we get something greater than 1 and it's this graph, or if it's less than 1 and it's this graph. So let's get our equation. Our equation is y equals 3 to the minus x. And let's test a positive value. So what's a positive value? I reckon 1's a really easy one. So let's test 1. Y equals 3 to the minus 1 when x is 1. All right, so you can do this on your calculator if you like. Your answer is 0.333 blah, blah, blah. Is that greater than 1 or less than 1? It's less than 1, so it can't be this graph up here because everything here is greater than 1. It has to be this graph because everything after the y-axis, everything that's a positive value of x is going to be less than 1. It's decreasing. And we can also see that just by looking at this and going, oh, this is a negative, which means it's going to be decreasing and it's going to look like one of these graphs. And we also know that it has to cut the y-axis at 1 because 3 to the power of 0 is 1, 5 to the power of 0 is 1. Whatever this number is, if it's to the power of x and x is 0, well, it has to be 1. So for a spanning tree, we know that we need to go through every single vertice. So a spanning tree has to include every vertice in the network. And it doesn't have to all be connected. So that's what gives it that tree name. It's like the branches sort of branch out like that, and they don't have to be connected to other branches. And it can't have any of these loops like this, and it can't have any cycles either. So something like this here, this is a cycle. This over here, this is another cycle. We don't want any of these closed sort of circles, or we just don't want any closed shapes. We want it to be open like a tree with tree branches. So what do we have here that we can cancel out immediately? Well, I can see this loop straight away, so I know it's not A. Can we see anything else that is closed off and has a fully closed shape in it? So C over here, we've got this closed shape here. This is a cycle, so it's definitely not going to be C or A. Now we've got B and D. How are we going to narrow this down? So the first thing I mentioned was that a spanning tree has to go through every vertice. So let's make sure that both of these are including every single vertice. So we've got H, I, J, K, L, G, H, I, J, K, L. I'm just going to go in order of the alphabet so I can remember. So G, H, I, J, K, well, this one doesn't even have L. So we know it's not B because it has to include every vertice. So the only option left is D. Let's just check it's got every vertice. G, H, I, J, K, L. And it's got no loops. It's got no cycles. This looks like a tree to me. So our answer will be D.